Swayam Prabha. Digital India. Educated India.
Welcome to the second lectures on fluid mechanics. As last class we discussed about the basic concept of fluid mechanics and the introductions level. So today I will just have a recap of the previous lectures, then we will go for the two concepts what is prevails in fluid mechanics is microscopic and macroscopic, that the things we will discuss more details. Then we will go for the fluid properties like density, specific volume, specific gravity and the specific weight, and very interesting well known Newton's laws of viscosity, that what today we will derive at both the concept at microscopic level and the macroscopic point of view. And then we will discuss about what is the effect of the temperature and pressures on the viscosities, then the surface tensions. So let us have a recap of the previous lecture, the first lectures what you said it discussed. In fluid mechanics, as you discuss is that we are talking about the behavior of the fluid either at the rest or in the motions, and also the interaction of fluids with the solids or other fluids at the boundary. The more important concept what we have discussed is no slip conditions. That means when a fluid is a moving fluid in a stick with a solid surface, the velocity of the moving fluid is equal to the velocity of the solid surface. That is what at that point the no slip conditions exists. So that is the very basic concept, and that is what governs the fluid flow process, what we will discuss many times about these no slip conditions. As in the last class I discussed so many problems of the fluid flows, considering from engineering problems, flow through the pipes, the wind blow over the mountains, all what we can categorize or classified into different groups like external flow, internal flow, incompressible flow, compressible flow. And when you talk about incompressible flow and compressible flow, the basic properties of the density, that was the key factor decides us whether it's a flow is incompressible flow or the compressible flow. Similar way, when you talk about the time components, if it's the time, the flow properties do not vary with the time, then we call the steady flow. That means we can consider some of the fluid flow problems where the flow properties do not vary with the time. So that is the assumptions we can take it and solve the problems. So that is what the steady problem. Similar way, we can have the unsteady flow where the flow properties like the density, velocity, the pressures, they vary with time within the flow domains. In that is the case, then we have the unsteady flow. Then we have also discuss about one dimensional, two dimensional and three dimensional flow. That is what is talk about when you talk about any flow conditions, it is the three dimensional flow, but we can approximate it or into one dimensional flow behaviors based on the flow characteristics, two dimensional flow behavior as we discussed in the last class. And more instantly again I have to talk about that what in the last class I have given you just a definitions for the laminar flow and the turbulent flow. The laminar flow in a pipes or any domain where it's well behaved fluid or the orderly behaved flow, the smooth layer type of the flow behaviors happens it. And when you come to the turbulent flow where you have a lot of eddies formations will be there is a lot of flow exchange between the two layer of the fluids and the mixings will be there, that is what is the turbulent flow. And the more detail we will discuss it as we proceed in the lectures on laminar flow and the turbulent flow. Now let us consider coming to the fluids, the definitions of the fluids. And if you look at if fluid is a composed of the molecules in constant motions and collisions, okay, then you can just think it that the fluid flow what is happening it, that is what the representations of a million number of molecules are in motions, also they are colliding each others. If that is the conditions, like for example, if you look at these figures, here I am very zoomed view of molecules what we are showing it, where he is having some sort of for oxygens 3 to 10 to the 16 number of molecules are present in a just a millimeter cube area volume. So that what is indicates the how many molecules are there if you take a 1 millimeter cubic volume of oxygens. That means so many molecules are there, and these molecules are having the random motions. Okay, there will be velocity here and here. So they have the random motions each others, and they are colliding each others. Okay, the manifesto what we get is the density variations or pressure variations or the velocity variations. These are the molecules, the gross characteristics what we get it at the density or the pressure variations or the temperature variations. Also their relative properties what we will discuss about viscosity and all. So if you look at that, if these are the molecules are there in a 1 millimeter cubic millimeters, this many molecules are there, they are having the random motions, they are colliding each others. Very basic things which call that what is the average distance traveled by a molecule before a collisions. That is what is called the mean free path. Mean free path, what's there, what is the distance travel on average distance traveled by these molecules before its collisions with another molecules. That is the mean free path. This is what gives us a very interesting phenomenon to us. Like for examples, if I look at the number of oxygen molecules in 1 millimeter cube is 3 into 10 to the power 16, but the mean free path of these oxygen molecules at 1 atmospheric pressures at the 20-degree temperatures is equal to 6.3 into 10 to the power minus 8 meters. So if you look at that, this mean free path is about to 200 times of the diameter of oxygen molecules. That means there are a lot of void space are there, and the molecules are having random motions and colliding each others, and the distance between average distance traveled by the fluid the molecules here, the oxygen molecules is a 200 times of the diameters of the oxygen molecules. So lot of void space are there. So you can imagine it that there are fluid molecules are there and they are having a random motions, and there are the average distance they travel it. So these properties what is happening at the molecules levels, that is what is reflect us very interesting concept. What let us consider very basic fluid properties is the fluid density. Okay, that means that is what is the mass per unit volumes. That means if I consider a very tiny delta V, and that delta V is the sample volume for me, and if I consider that sample volumes, I will have the density the delta M by delta V, okay, mass per unit volume. That is the density what will be there. Now if I look it, as I am going to increase the delta V which is a sampling the volumes which is very less to go for the higher order, as these figures is showing it that this side I have the density, here is I have the sampling volume. Okay, let us consider it that the sampling volume delta V I have considered it to represent the density. If I have a delta V is very small, okay, and which is less than 10 to the power minus 9 cubic millimeters, you can see these values will be changed like this. That means when you have a very small the sample volumes, so the mean free path deviation, the molecular motion of the random motions, that what is changing the density value. That means indirectly it indicates that the number of the molecules within that small sampling volume, that what it changes drastically as instant to instant. As the number of molecules are coming in and number of molecules are going out, that what is give a random motions what is exhibited that within the fluids, that what is give a lot of variations of the density value, as the number of molecules coming in and going out, they are not balancing each other. That is the reasons you have the uncertainty, the density will vary drastically. These are not a time dependent component, but that's it will be vary as we will have the sampling measurement is lesser than a threshold value. Similar way, that is what is called the microscopic uncertainty, as the density vary considerably as we are sampling volume is lesser than this. But there is a limiting conditions like the delta V star, it is a limiting conditions. At that limiting conditions, if you look at these regions, the density fairly constant. That means what I am telling is that the sampling volumes, as we increase it at a particular limiting value, we can see that the density remains constant. That what indicates is that with that the sampling volumes, the number of the molecules coming it as a random motion into that and going out more or less balanced each others. So we will have the density, the constants. So we have to do a measurements, or we have to do the analysis beyond this point, then the density remains fairly constant for regions, which with respect to the sampling volumes. I am talking about with respect to sampling volume. But if I increase the sampling volumes, it is much larger, okay. It could be 1 meters or the 2 meters like this. So I can consider a big sampling volumes. So in that case also will not have the density constants, the density will vary it. That means we call the macroscopic uncertainty, that sampling volume is too large, that like if you consider this is the room is a sampling volume for me. See, in that case what will happen is that the density variations within this room, that what will play the rules, that will not have a constant value. So the density will vary within this the sampling volume. Because of that, if I consider the average density over for this sampling volume will be different than the actual density at the center of the sampling volume. So that is the reasons we will have the variability, the spatial variability, the locations variability is too high. This sampling volume will not represent the density value what should be the required for the analysis. So if you look at the two type of uncertainty happens it with respect to the sampling volumes. One, if it is very lesser than the limiting conditions, where is 10 to the power minus 9 millimeter cube, you will have a microscopic uncertainty, and if you go for a very large sampling volume, you will have a macroscopic uncertainty, microscopic and the macroscopic uncertainty. So that's the reasons what we do it. We work on the regions where the density doesn't varies with the sampling volumes. So that means our sampling volume such a way that the fluid characteristics doesn't vary, as the random motion of the molecules are not playing the major roles to varying that properties. So that's the indicator here is the sampling volume, which is 10 to the power minus 9 millimeter cube. More often in engineering applications, like any measurements we do it much larger than that. So any correct analysis what we do it for engineering applications, that the sample volumes represent much larger than this part. So we can consider it that the sampling volumes what you have neither to be a too large or not too tiny, it must contain the million number of the molecules, so that the random behavior of the molecular motions, that the collisions, that what will not reflect in our characteristics or properties of the fluids. So that's in a mathematical I can define it, that we are looking the density where the limit is tending, this sampling volume tending toward the limiting velocities volumes of these things. So that is the density, the properties. So that means that's what we consider, there is a density variations, but that density variations, our sampling volume is so large near to the limiting conditions, which does not have a effect of microscopic or macroscopic uncertainty. In that regions we can consider the density, any fluid domain what I have considered it, okay, any fluid domains I consider it. So if density is varying, let be this is 1000 kg per meter cube, this may be 1200 kg per meter cube, this will be 1400 kg per meter cube. These lines are representing 1400 kg per meter cube, 1200 meter cube and this. So on this fluid volume, fluid domain, we can consider the density is a function of space dimensions, that is x, y, z, and also the time density. When you consider as a continuous and continuously differentiated functions, that means it is now very easy, we can use the integral concept, differentiation concept, as it is a functional behavior with a space and the time. Be remember that if you have a microscopic or macroscopic uncertainty, you cannot define it is a continuous functions. So now we called as the fluid as a continuum, because we can use a continuous functions of the density of flow properties, differentiated functions to define that flow process. So we define as the fluid as continuity. So similar way, as the density is having a continuous functions, we can define is the pressure is also a continuous functions of the space and the time. The velocity, scalar velocity component like vectors u, v, w can have a space and the time, the space and the time, and space and the time come. So all these component, the fluid flow characteristics, we can define in a space functions, also the time functions x, y, z and the t, provided consider as the fluid as continuum. That means we do the analysis of the sampling volume such a way that the randomness behavior of the fluid molecules and their collisions are not give any uncertainty at microscopy scale and the macroscopy scales. But the some of the case we cannot apply this fluid as a continuum hypothesis. For examples, if you go to very high altitudes in the space, you will see that pressure will come to very close to the zero. So that is what the rarefied gas conditions, where the pressure is very close to zero. There we cannot apply this, because the mean free path motions of that type of gas is much higher order as compared to the normal gas and the liquid what we consider in common engineering problems. So, that is the reasons we will cannot use this continuum concept of rarefied gases where the pressures is close to the 0. Exactly same way the microfluid applications, that the fluid devices at micro and nano scales, we cannot apply the continuum hypothesis. There are a lot of advanced research advances going on how to handle the fluid flow which does not follow the continuums hypothesis. Okay, let us go for the fluid properties. One of the basic properties, as you know it, mass, okay, or the weight of the fluids. As you can know it, in different fluids have a different mass, like the mass of the air, mass of the waters, mass of mercury, that what will be the different. So, different fluids what we use it, they have the different mass, and any fluid flow problems analysis, the mass is the primary component which we use it to analyze the fluid flow problems. That is the reasons, as I told earlier, that if I consider a small volume of the fluid, the mass of the fluid, if I measure it, okay, as the volume of the sampling volume is larger than the limiting volumes for the continuum hypothesis. So, if I consider that part and get a mass of that fluid and do a mass per unit volume, that means we are, that is what is the density. So, mass per unit volume, if volume is 1 unit, any cube of millimeters or cube of meters, that whatever the mass, that is what will give us the volume density. So, that is what we can get it in terms of kg. That means, if I take a 1 meter cube of water, whatever the mass of 1000 kg, that what will be the density for me, that means 1000 kg per meter cube. So, the very basic thing is mass per unit volume, that is the density. I am just re-emphasize that any fluid flow problems you do it, the first foremost requirement is to calculate what is the mass of the fluid. So, if I know the volume of the fluid and the density, I can compute the mass. The very simple way, like if I know the volume, we can convert it that, and there are the tabulated values available to that. But there are the problems what like in gas flow and all, where we do not talk about with respect to the mass per unit volume. Here we talk about mass is a fixed quantity. That means we are looking at the volume per unit mass. That means 1 kg of hydrogens, what is that volume is coming it, as volume is a variables in a much higher variable as compared to mass in a gas. So, we use the specific volume, that means the volume per unit mass. Okay. This is what the density, mass per unit volume, definitely is reciprocal to the specific volume is reciprocal to the density. So, you will have the unit is the cube meter by the kg. But many of the times either you know the mass or the density, or you know the specific volume, you can solve the problems. But to make it a very simple way to represent it, which is in one is heavier and the lighters. Okay. So, in that case we have to consider a reference liquid or reference gas. As we will, I will focus more on liquid. We consider the reference liquid is here is the waters. Okay. That means we are looking at the ratio of density of a liquid to the density of a reference of liquid, which here is waters, that what is give us the specific gravity or relative density. So, this specific gravity gives us it's a heavier or lighter than the with respect to the waters. So, like a specific gravity of the mercury is 13.6. What does means that it is a 13.6 times heavier than the water. That's what indicate for us. So, there is any of the textbook you can have you can see the table of specific gravity values or the densities or the specific volumes value. Most often, as I say, that either you talk about the mass or you talk about the weight, that means force due to the mass. What is the gravity force is acting for that. We do the analysis for that. That's what is we consider the weight per unit volume of a substance is the unit weight. That means this is very easily any fluid flow problems. So, what is the weight of the fluid is there, that what we can compute it just multiplying the volume of the fluids. So, specific weight, and any relationship ways it will be the mass into the accelerations due to gravity. So, the specific weight is rho into g, that is what the specific weight of this thing. Now, if you look at these examples, which are very simple examples what we have given here, that there are the layer of the fluids are there, and which is having a density rho 1, rho 2, rho 3 and rho 4, V1, V2, V3, V4 are the volumes. As you know it, you will have a heavier liquids here and the lighter liquids you will have here. Okay. So, you have a heavier liquid and lighter liquid as basic concept is that. So, that means your the density of rho 1 will be larger than the rho 4 as this is indicating that. So, how much of mass of the fluids are there? If I take a, like for example, I take it, what is the mass of air of this room? I can get what is the density of the air here and the volume of this room, multiply that, I will get the mass. And if I looking the weight of the fluid, that what will be the mass into the accelerations due to gravity, that what will give us the weight. Very simple concept, the density multiplications of the volume, that what will give a mass, mass into the accelerations will give us the gravity force, the weight acting on that fluid mass. Similar way, as I said it, if I have a layer of the fluids are theirs, okay, in generally it happens, it is a layer of the fluids which are there, they are having the density variations. We can just compute it, what will be the weight, is the sum of the weight for each zone. We can compute for zone 1, zone 2, zone 3 and zone 4 and sum up that what with the total weight of the total fluid columns. So, this is what very simple examples what I have given it. I am not highlighting what is the density of different fluids, which you can refer to any fluid mechanics book. Now, let us go to the very interesting concept, the Newton's laws of viscosities, okay, which is very simple common laws of viscosity which we used for solving many of the problems in laminar and also approximate for other flow conditions. Let us talk about this Newton's laws of viscosity. I am presenting you in two ways. One is microscopic analysis and the macroscopic analysis. If you look at that, you have the plate, okay, if you can look it, which is at the rest conditions, and you have either in the top another plate is there where you are applying a force F and the velocity v is it's moving this plate. As we know it that whenever we have the fluid flow conditions, we will have the no slip conditions. That means at these locations I will have the velocity 0. At these locations the contact of the fluid particles on the solid surface will give a velocity equal to the velocity of the plate. So, I have the velocity v here, I have velocity 0 at these points. So, no slip conditions prevails for these 2 points as we are dragging these ones. Now, if you look at, if I consider A and B 2 locations, okay, and in these 2 locations I consider a small representing volume of the fluids which is moving with, let be a V2 velocity and the V1 velocity. Try to understand it, that I have the 2 fluids pockets, one is moving with V1, within that there are million number of molecules are there. The similar way, the V1, the next layer of the packet, what the fluid is moving with a million number of molecules is moving with V1. So, if you look at the nature wise, when the 2 packets are moving it, one is a higher velocity and another is the lower velocity. At this interface, what we can say that it is a virtual interface, there is no real interface is there. We make it the flow representations as a 2 packets, okay, packets A and the packet B, they are containing million number of the molecules which are in a random motions and colliding each others. So, if that is the conditions, then definitely the basic concept what it comes it, these fluid molecules what is there, they are crossing each others going off, okay, from layer B to the A. As they are, the molecules are coming from the B going to A, they are transporting the mass, also they are transporting as a momentum flux to the next level. Because of that, the packet B will try to reduce the velocity of B1, packet A, okay, just like that in nature what will happen it if somebody is running fast and other is slow. So, slower one will try to make it other to reduce the speeds, okay. Exactly same way happens here, that molecules at the B packets which are moving slower, they will try to reduce the velocity of the flow of the A. Whereas the A, what will do it, that the same way the molecules in the A packet, that what will be again exchanged to the B, they will try to increase the velocity of these packets, on average the velocity of this packet to this. So, in these the artificial boundary layers, they are, as we cannot see it, we can visualize these problems, okay. We cannot see these things how the molecules are happening it as the random motions are happening it or colliding each others, that what we cannot see it, but in conceptually there are the mass flux are going up and the momentum flux is exchanging between that, and the momentum flux mass exchange what it happens between these 2 layer of the fluid packets, that what will be cause a force on these layers, these interface layers, and that force will be act like a shear force, a resisting force between these 2 layers, that what will be act like a resisting force between these 2 packets of that. And that what it happens it, the layer A tending to reduce the velocity, okay, due to the molecular mass and the momentum flux exchange, whereas the layer B due to this exchange project tending to increase the velocity, so that at the larger time step or this process if it goes on, after certain time maybe this 2 velocity is coming to equilibrium, that means they will be the same order, same value. So, looking these the mass exchange and the momentum exchange of the molecules at these the artificial interfaces between 2 packets of the fluid packets, we can see that definitely there will be the force will be act on that interfaces as the momentum flux is crossing each others, and shear stress will develop at this interfaces level. And many of the studies the experimentally establish that this shear stress will be have a directly proportional to the velocity gradient. Okay. If the more they have the directly proportionality. Okay. Thus, that means more the velocity gradients is there, so you will have the more shear stress, but it has a directly proportionality quantity, and the proportionality is known as the coefficient of viscosity or dynamic of viscosity. The constant of proportionality constant is known as a coefficient viscosity. So, that means it varies from the fluid to fluid, because their molecular motions, the exchange of the moleculars, the momentum flux, the random motions, all it depends upon molecular structures of the fluid. So, when you apply a shear stress or a resulting a velocity gradient, which will be will have the shear stress formations, that what as a resistance of the two layers, that what will be a constant proportionality, which is a coefficient of viscosity, which varies from fluid to fluid, as if you look at the motion of the molecular point of view, considering as a mass exchange of the molecules and the momentum exchange, that what will be there. So, the fluid to fluid will have a variability of the mu value, that is a coefficient viscosity, which is as equivalent to that if a two solid objects are there, as one is moving and others, as you know that there will be a frictional resistance. So, the hypothetically the same conditions are happening here, that if I consider two fluid packets and if they are moving with having a motions, the molecular motions between these two artificial layers, we will have the shear stress formations, and that shear stress formations will have the proportionality to the velocity gradient, and that proportionality constant is a coefficient of viscosity, or some of the book is referred as the dynamic of viscosity. And what you can know it, what will be the unit of these ones, you can put the unit of shear stress, the dynamic, the velocity gradient, you can see that it will have the mass per length and time. So, that means for a CGS systems, the gram centimeter second systems, we for a 1 gram per centimeter per second, that what we call the poise. That means 1 poise is 1 gram centimeter per second. That is what we consider it, the poise is in a CGS systems unit of the coefficient of viscosity or dynamic of viscosity. Yes, let us consider microscopic point of view. If I consider the same fluid flow through a parallel plates, okay, one of the plate the velocity is 0, which is at the rest conditions, another the top plate is moving with the velocity v. So, as a microscopic point of view, I am not talking about the molecular motions or exchange of the molecular motions or the momentum flux, that what is resulting a shear stress. Here what we consider that fluid element, that means I consider some space of A, B, C, D, this is what the fluid element. That means whatever the fluids are there, that regions I am defined as a fluid element. As you know it, that at the A point we will have the velocity v as the no slip conditions, at the B point we will have velocity 0. So, velocity, assuming it will have a linear velocity variations from B to A, that linear velocity from 0 to V, as the y increases, the velocity will increase it and maximum velocity will be the V. If it that the conditions. Now, if you look at that, if a point which is the y distance from the plate which is at the rest conditions, you will have velocity u. Okay. So, as a linear proportionally, we can find out what is the velocity of that ones. So, next one is the velocity lesser than that, or above one will go moving with the fluid is more than that. So, if I has a linear velocity distributions as we assume it and as we got it some of the parallel flow conditions, after delta t time this fluid element will be deformed as a angular deformations will happen it, that there will be angle theta will come it at the B and E, F and D. That is the new positions of the fluid element after delta t time, and the angular deformations at these points is delta theta, similar way the delta theta at this point. So, at the delta t time we have a angular deformations of delta theta. So, consider a very simple geometry of these problems. I can consider this distance of AE is V into delta t, divided by the L will be the tan delta theta, or since delta t is very small, I can consider delta theta equal to V delta t by L. Okay. So, that is what we will consider. Just rearranging that, we can see that the rate of change of angular deformations of this fluid element is equal to V by L. V is a constant, L is the thickness of these two plates, that is a constant quantity what is coming it. Now, if I consider at the y distributions and the angular velocity distributions, if I consider it, I will get it the small u, the velocity at these points and ratio of the distance as a linear velocity distributions concept, we can get it u by y v by L. Simple geometry of this what give us relationship. That is what if I differentiate it, I will get it this part. Be remember, this is what is indicating us is that the velocity gradient. If I consider this the y directions, how the velocity varies along the y directions, that is the constant which is equal to the shear strain rate, the shear deformations per unit time. So, we can now consider it that the shear rate, strain rate and the velocity gradient is equal for these conditions. These parallel flow conditions, when you have a velocity is linearly distributions, the shear strain rate and the velocity gradient, they are equal. So, now we are coming to the exactly the solid mechanics concept, the stress having the proportionality with the strain. But here we are talking about the stress is a proportionality to the strain rate. That means, the change of the shear strain rate with respect to time, not the absolute value of the shear strain. That is the basic difference between the fluid mechanics and the solid mechanics. So, same stress strain relationship we are doing it, but in this case we are telling it that the shear stress is a proportionality to the shear strain rate, and that is the Newton's laws of viscosity, that shear strain is having a, this experimentally proved it, that is what it happens is shear strain is a proportionality to the shear strain rate. Again I can emphasize to that shear strain rate, not the shear strain, that is the difference between the fluid mechanics and the solid mechanics, as they have the proportionality, and we can define as the shear stress is proportional to the velocity gradient, and the same way we can define it that proportionality constant is a dynamic viscosity or coefficient of viscosity, the tau into mu into dy by dy. So, this is the same concept, we can use a fluid element at the microscopic levels, define this relationship between the shear stress and the velocity gradient, or at the microscopic levels the fluid molecules movements in terms of mass and momentum exchange, also the experimental finding also give the same concept, that the relationship between the shear stress and the velocity gradient. Be remember it here we are talking about velocity gradient along the y directions, and the shear stress is a normal to that, that the point what you can look it. So, that is the shear stress is equal to mu in dy dv. This is very basic equations used to for solve many of the problems. If you just have a basic concept is the stress is having a proportionality constant with constant proportional constant, that is what is the dynamic viscosity of the coefficient of viscosity. Now let us commit that how does the temperature affect on the coefficient of viscosity. Now we have to look at the molecular levels. Okay. So if you look at these molecular levels, when you talk about the liquids, they will have a molecular bonding forces between two molecules. Okay. But that word is much weaker when you talk about the gases. So gas are more random motions as compared to the molecules are more random motion as compared to the liquids. So when you increase the temperatures, okay, or increase the pressures, like if I increasing the pressures, that means I am compressing the fluid things, a fluid volumes, I am just compressing it. As I compress it, whether these molecular motions, exchange of the molecular motions in terms of mass and momentum, does it change drastically? What is experimental find that if you let it this now having a 1 atmospheric pressures, this is the, if I increase to the 50 atmospheric pressure, the coefficient of the viscosity on this area room will not change that high, that may change it less than 0.5% of the at the 1 atmosphere value. So change of the pressures, if you try to understand it, that what does not change that significantly the molecular motions or exchange of the molecular motions, mass or the momentum flux, as mu will not change drastically. So you look it in terms of the molecular motion as a mass exchange and the momentum exchange. But if you look at the temperatures related is that how much of collisions are happening. If you look at the fluid mass or the liquid mass, whatever the temperature of the fluid I am getting it, that is indicating me the how the molecular motions are sustaining that temperatures. So because of that, it is when you increase these the temperatures, the definitely you increase the random motions of these things. Okay, for liquids, let's look at that change of the pressures will not change that significantly the coefficients of viscosity, which represent as a proportionality constant of mass exchange of the molecules or momentum exchange of molecules from one layer to other layers. If you increase the temperature, which manifests the molecular motions to sustain that temperatures. In that conditions, what it will happen, it will reduce the binding force, the intermolecular binding force between two molecules. Because of that, there will be a decreasing trend of coefficient of viscosity. If you look at respect of the molecular mass motions, and that what is causes as the mass transport and the momentum flux transport. If that the conditions if you are looking at, then increase of temperatures will reduce the intermolecular forces and definitely to reduce the decreased trend of the mu values, like this case what is shown it here, decreasing trend will be there. That will vary from the liquid to liquid, we will discuss that. Let us talk about the gases where the intermolecular binding force are not that significant, the molecular motions are much the random much the higher order as compared to the molecular motions in the liquid. The same way the change of the pressures will not much give a significant order of change of the dynamic viscosity, but the change of the temperatures, if I increase the temperature like 20 degree to the 40 degree or the 40 degree to 100 degree centigrade temperatures, then there will be a increases the random motions of the molecules. As it is increasing the lot of motions of the molecules, the definitely it does the mass transport, also the moment transport. Because of that, you will see that in a gas, as is given here, the viscosity and temperatures, the viscosity increases as the temperatures increases. Whereas in the liquid, because the temperature increase reduces the intermolecular forces, you will have a decreasing trend. So, the liquid and gas, that what their the coefficient of the viscosity, that's what varies with respect to temperature. One is increasing trend, another is decreasing trend. Any of the gas or the liquids, we can find out what is this effect as the functions. Now, if you look at this for the gases already established by US standard of atmospheres, that what the Sutherland correlations technique, which gives a relationship between the dynamic viscosity and the temperatures. That is what for, and A, B are the constant coefficients. These coefficients will be differ from the fluid to gas, and that what conducting any experiment we can get it what is the value of the A and B as we are increasing or decreasing trend with respect to the mu value. So, simple experiment of the gases with the different temperatures and using a viscometers, we can quantify it how the dynamic viscosity varies with the temperature. As I said it will have an increasing temperature, increasing with the temperatures, but this A, B coefficients will vary from gas to gas. Similar way, if you for the liquids, if you look at that, it will have the 10 to the power the functions A and B and the C will be the constants, and these things what we can compute, get it from experimental or any reference book and textbook. You can see for the different fluids you will have a different value of ABC for the gases, and this for the liquid and gas we have a different functions as the temperature dependent functions of with a dynamic viscosity and the temperatures, and these coefficients will be differ from fluid to fluid. So, based on the gas and the liquid we will decide that which equations you have to follow it, what are the coefficients. Mostly it is available in any textbook and the reference book. Let us come to the next one. How does the coefficient of viscosity vary for different fluids? Let us take it same very simple equations what we have defined it, tau equal to mu into dy by dy, the velocity gradient. If it is dy by dy equal to the 1, which means the velocity gradient is unit. That means the shear stress what will be equal to the mu. This very interestingly what is giving it that if I have a systems where we can create it a velocity gradient is equal to 1, the whatever amount of the shear stress, that what will be the coefficient of viscosity. That means we can easily compute what will be the coefficient of viscosity if you have a just make a dy by dy. So, this coefficient of viscosity can consider as a force, as a shear force when you have the velocity gradient is equal to 1. So, if you look at that concept, that means if I plot the rate of deformations, the velocity gradient and the shear stress at these points, and if I have the two common fluids like air, waters and the oil, as you experience is that whenever you drag any solid surface on water or air or the oil, definitely you need a more force to drag when you are dragging on a oil mass as compared to the water. When you drag that object in a waters, definitely that what will be a more force required. That means it has a more frictional resistance what we get it when you go for the water as compared to the air. So, that's the very common way every time we experience that when you different fluids give a different drag force, that means different amount of frictional resistance what we define in terms of shear resistance here. The shear stress and the rate of deformations, if I look it and if I look at the slope of this curve, it gives me the mu value. That is for air, if you look at the value is 0.00018. When you talk about the waters at atmospherics and the 20-degree temperatures, you will be 0.010 case, but when you come to the the engine oils, okay, which will be 0.10 kg. So, if you look it from these figures, their order, you can understand it as how the coefficients varies from the fluid to fluid, and these slopes are indicating for us, and these are constants. So, they have a straight lines what we will get it, and the slope will be give us the coefficient viscosity. The fluids, those follow this relationship, this constant, the proportionality relationship between the shear stress and the velocity gradient, we call them Newtonian fluids. Okay, that group of the fluid flow problems we call Newtonian fluid, where you have the shear stress causing by any shear forces is directly proportional to the velocity gradient or the shear strain rate. Those fluid flow problems we call the Newtonian fluids. That means what? The coefficient of viscosity, which is a directly proportionality constant, that does not vary as the rate of deformations are changing or the time is changing it. So, that is a constant. So, that is the reasons we have a directly proportional, and we can get it a very simplify the shear stress is mu is equal to mu times of the velocity gradient. Most of the common fluid flow problems also follows the Newtonian fluids, but some of the case it does not follow the Newtonian fluids. So, we call them non-Newtonian fluids or fluid flow problems. In that case, what you do it, like for examples as given here, the rate of deformations and the shear stress. If you look at this straight line, what is representing that straight line, whatever if I have the straight line between these two relationship, and in this graph which are Newtonian fluids. But there are two types, the different type of fluids will be there, like if you look at this pseudoplastic and dilatant. Okay. In case of the dilatant, if you look at the slope of these curves are increasing it, okay, at rate of deformations is that. That means if it is a dilatant objects, okay, of the fluids, in that case as the deformations rate is increasing, slope of the curve increasing, and that slope of curves is we call, don't call it the viscosity here, we call apparent viscosity. It is not, this viscosity has a depending upon the deformations rate. So, that is the reasons we call them as apparent viscosity, which is the slope at the particular deformations rate what we consider it. That what is, if it is increasing with the deformations rate, then what is happening it, the shear thinning process is happening it. You can understand it that more shear force is necessary as you go for more the slope, that means you need a more shear force to do the same amount of deformations as compared to the point A and the point 2. So, shear thinning process are happening it. That means as the deformations rate of deformation increases, the more shear forces is required to do the same deformation, 1 unit of deformations rate as compared to the deformations rate when it at the low level. So, this is a thickening process happening. Okay, the more the shear forces we did it. But if you look at this curve, which is a pseudoplastics, what it indicates that the slope is decreases as the rate of deformations is increasing trend. That means you need a less shear force as at the higher deformations rate as compared to you look at the deformations rate when you have the low deformations rate, you need the less as compared. So, your slope is changes it, the shear force what is necessary is going to decrease it for doing the same amount of deformations at two different rate levels. That means is a decreasing of this dynamic of viscosity with increase of deformation. So, thinning process happening, okay, and shear thinning fluids happening, and that the process happening, the shear thickening and the thinning process happening, the more forces is there. There are the fluids like the toothpaste and all, as you know it, when you apply a force to a toothpaste, So initially it doesn't come out. That means it need a limiting force. Okay, that limiting force should be there. That what is the a finite shear stress there needed that. After that the flow starts it. That's what it happens if you just squeeze a toothpaste. You can feel that initially when you apply the low force, there is no toothpaste is coming out. But when you apply more and more force, after a certain force you look at the toothpaste is coming out. The fluid is starting the flowing it. So responding to the shear force as deformation starts it. So that is the reasons you will have a limiting finite stress, shear stress. After that you will have the shear stress and the rate of deformations will be there. This is what Bingham plastics, what we talk about, which resists a finite shear stress and deform continuously when shear stress exceeds this yield stress. Okay, that is the behavior what you do it with the toothpaste flow mechanisms what is there. But in case of pseudoplastics, we have a pants polymer solutions, whereas dilettant is basically the solutions with a suspended starch and the sand. So in this the presentations what I am talking about, that the coefficient of viscosity which is indicates us that in a fluid element how the deformations takes place between deformation rate and the shear stress relationship can be linear, can be non-linear. If it is a non-linear, we talk about non-Newtonian fluids, and depending of the slope increasing with respect to the deformations rate, we call shear thickening process or thinning process, or we have a particular threshold value. After that the fluid start deformations, shear deformations things, then we call Bingham plastics. So the basically you try to understand it that we define as a Newtonian fluid, non-Newtonian fluids, the coefficient of viscosity which is directly proportionality constant, or we consider as a apparent viscosity when defining the fluid flow problems if it is a non-Newtonian fluid flow problem. Let us discuss about another properties of the fluid is the surface tension. As the name implies that at the interface of the two fluids or fluid with two liquids or fluid and the gas, what it actually happens it, if you look it that way, that I have the liquid molecules, if you look at these figures, okay, I have the liquid molecules and this is the free surface, I have the gas. So if I look at what is the intermolecular forces is there, okay, like for example, if the fluid is at rest conditions, the molecules at these points is having the attracting force between the surrounding molecules. There is a same molecules are there, so the cohesive force are acting on this. So these cohesive force are making these fluid molecules in moment concentrations. But when you have the at the surface levels, if you look at that, these molecules will have the cohesive force, the molecular bounding force between the two like molecules, and the adhesive force between the gas molecules and the water molecules. So those will have the adhesive force. See, if you imagine it that if this force, the cohesive force is much larger than the adhesive force what is there, that means the molecules which is at the surface, they are going to have a net imbalance force is going to work it. Like you have a surface in which the top of the molecules, they are having a pulling effect of the cohesive forces what is working it, bounding forces acting on that. So this the surface will be act like a elastic membranes, that means you just stretch it, give a force, the more net force is more. So that's what is a will be like a stretch electric membranes with having the tensions. So for example, if you look at that, you have a rope which connected with a two pillars, and if you apply the force uniformly, you will see that there will be a tension force will be act on that. So, the similar way, as we can visualize that even you have the molecules at the surface, they have a net imbalance force between these, the cohesive and adhesive. Because of that, that surface will be act like a stretch elastic membranes and under the tensions. That is what will be cause it. So, that because of these effects, the force what will be resultant per unit length will define as a surface tension forces. Okay. So, this is what it happens it, because of that if you look at the small insects, they can walk on the waters because of the surface tension forces, that what is give a the force component, because of that small insect they can walk on the on a water, and even if they are having the densities more than that, that is because of the surface tension forces, that what resulting surface force can result in that ones. It has a lot of applications of surface tension forces, but here I will not give a more emphasis on that. And if you look at that as the surface tensions is defined as a force acting per unit length, and that what will be Newton per meters, and the at the surface tension of the water with air interface is a 0.07 per Newton per meters. And if you look at the molecular perspective view that as the temperature is going to increase it, so you will have a decrease of the cohesive forces. As the cohesive forces decreases, you can know if the net force is going to decreases. So, resulting effect, the surface tensions will have a decreasing trend. So, we can, when you have an interface between the liquid to liquid or the gas to liquid, you will have the surface will be act like a elastic membranes with a tension forces. That is what we call the surface tension, and it has a dependency with the temperature. As increasing of the temperatures, that is what reduces the cohesive forces, and as a result the surface tension force also decreasing trend. If you have the surface tension, if you can now doubt, there will be a net balancing effect of the force component, which results as the pressure difference. Let us consider its the surface tensions is given very simple examples of raindrops. Okay, any raindrop, if you look at that, if you take that drop and make it two splits, at this the interface surface there will be surface tensions is working it. The surface tensional force is acting between the water and the air. I have considered a water droplet. So, if I consider the just half the things, if I consider this pressure inside is P liquid and the P gas, the outside is P gas, there will be difference of the pressures because of these tensional forces. And if I just equate the net force acting on this, the pressure into the area, that is what is the net force will be acted, there will be a pressure difference will be there. That what will be the force per unit length, and the length is a circumference on which the surface tension is working it is a 2 pi r into the surface tension, this force will be equated. So, similar way we can have a water droplet, we can have a soap bubbles, we can look at the the surface and find out what will be the surface tension force. This net force, the balancing, you can result as a pressure difference what it happens it, and you can compute the pressure difference if you know the surface tension, if you know the radius. Next interesting point is coming is that if a liquids interfacing with the solids, whether it will be wet or not wet, the wetting condition or not wetting condition, that what is a interface between the three things. Like if you look at, there is a interface between liquid to the gas, the liquid the solids, and that what is a at equilibrium at the point of the contact, and that equilibrium force is make a angle of resulting force the contact angles. So, the surface tension between the gas and the liquid and the solid, this net force what is acting here, that makes a angle to that. This is a what? Angle of contact. So, you can look it, if you take a liquid and you have the angle of contact more than 80 degrees, more than 90 degrees, then this liquid will not have, will going to wet this solid surface. Whereas, if this angle is less than that, this liquid can come into the solids. So, that can come into the solids and can have the wetting prods. So, very simple way we can find out which are the liquids going to wet the solid surface or not based on the angle of contact. The mostly this the resolutions of the surface tensions for the force because of the gas and liquid and the liquid and solid interference. We are not going more details because as you have a more understandings if you are looking for surface tensile for mostly this chemical engineering and all, but here we will not go more detail here. So, with this let me conclude this lecture 2 and with the summary is that the very basic equations is that we derived today, which is called Newton's laws of viscosities. That what we have looked at the microscopic and macroscopic point of view, the molecular motion point of view, or deformations of the fluid element. That what we have considered to define the shear stress and proportionally to the velocity gradient or shear strain rate. Then we also discuss is that how does the viscosity increases or decreases with respect to the temperatures or the pressures, that what we have discussed it, and some of the fluid properties what we discuss it with respect to the mass we discuss and the weight, we discuss the density, specific volume, specific gravity, specific weight, and the force acting on these interfaces, that what is a surface tensor force as interactions. I conclude that with this, I conclude this lecture. Thank you.